Hey guys, this is Professor Janacek, and I want to go over some examples of working with derivatives. I want to focus on mainly the power rule and the sum or difference rule. Let's take a look at the first example here. We're going to take the derivative of x to the ninth. That's x raised to a power. So we're going to use our power rule. According to the power rule at the top of the page, we take that exponent 9, put it in place of put it in the coefficient spot, and then write our variable raised to the exponent minus 1. So we have 9 times x raised to the x minus 1, 9 minus 1, so that's 9x to the 8th power. And there you go, the most basic example of the power rule. All right, example 2 looks kind of similar. We're taking the derivative d dx of 2 to the 5th. All right, so it looks like we have an exponent. However, in this case, we don't have a variable in there. It is 2, a constant raised to the 5th power, which, by the way, is the same as 256. That's just a constant, so we don't need the power rule here. We just need to take the derivative of a constant, which always, gives us 0. So don't be fooled by that one. Tricky. All right, how about example 3 here? We're taking, we've got d dx of 3/8 times the square root of t. All right, well, I noticed something. I'm taking the derivative with respect to x, but I only have a t over there. Again, that means I'm not taking the derivative of a variable. T, in this situation, would be constant with respect to x. I don't have any x's. If I take the derivative with respect to x and I don't have any x's, then I treat it like a constant. So again, that gives me a 0. Just taking the derivative of a constant. Again, tricky. Watch those. Now on to example 4. No tricks here, not really. We're taking the derivative now with respect to t of 3/8 times the square root of t. Okay, so I'm taking the derivative with respect to t, and I do have a variable of t in there. A few things to make note of, though. I think the first thing I'm going to do is write this t, instead of the square root, I'll give it a 1/2 power. Now I can see it's going to work using the power rule. Other thing I need to remember about this is that the 3/8 there in front can be kind of factored out first. So I'll multiply that on the outside, and then I'll take the derivative of t to the 1/2 power. Okay, so let's see. Taking that derivative, here we go. I don't need to write the derivative notation. I take the 1/2, write that there in the front, and then t raised to the 1/2 minus 1. So let's see, that gives us 3/16 times, actually I'll give myself a little more room, that's 3/16 times t to the negative 1/2. Of course, a negative 1/2 in the exponent there, that's the same thing as saying a 1/2 power in the denominator, but a 1/2 power, as we saw at the beginning, that's really just the square root. So we have 3/16 squared of t. Now that is okay, that is correct. However, let's go ahead and rationalize this denominator just to clean it up a bit. Multiply by the square root of t over the square root of t. So we get 3 square root of t in the numerator. In the denominator, it's 16. The square root of t times the square root of t is simply t. So there we go. Rationalized in a nice, lovely form. All right, example 5. We're going to take the derivative of this big, long polynomial. Now notice I'm taking the derivative with respect to w, and w is my variable, so no tricks here. But we do have this nice, long polynomial, 2w to the 3rd plus 9w squared minus 6w plus 4. So the way to work with this one is that and I'm going to write all of this out just to make sure there are no questions about what's going on. I'm going to take the derivative. This is using the sum or difference rule. I'm going to take the derivative of each term. Right, so the derivative of just 2w cubed. the derivative of 9w squared, minus now the derivative of 6w plus the derivative of 4. So that's the sum or difference rule. We've got both sums and differences going on in here, but we simply need to take the derivative of each term in that polynomial. All right, now let's go ahead and see what we get when we take those derivatives using the power rule now. This first term, whoa, where'd that go? The first term, we keep that 2. Then we'll take the exponent of 3, put it in the coefficient, take w, raise it to the 3 minus 1. Now again, you might be comfortable doing this. I just want to make sure that everyone sees what's going on. So if you're comfortable skipping the step, that's fine. I just want to make sure that it's clear. The next one, I'll keep that 9, bring that exponent there to the front, w raised to the 2 minus 1. Next we have a minus, and I've got the 6. Now here you can imagine that the coefficient, the exponent is a 1, so I'll again use the power rule. Take that exponent, write it in the coefficient spot, multiply it there in the front, and then in the exponent I subtract 1, so now I have 1 minus 1. And yeah, we'll deal with that in here in a second. And this last little bit, I don't have a variable. Okay, that's a constant, so I'll use my little constant property. The derivative of a constant is just 0. If we clean all of this up, we get 6w to the second power plus 18w to the first power, which I don't need to write, minus, now here we have 6 times 1 times now an exponent. In this case, we have 1 minus 1. That gives us an exponent of 0, which means this whole w ends up turning into a 1. So we have 6 times 1 times 1, so that's just a 6. And then I don't need to write that 0 there at the end. So there we go. The derivative of a polynomial. And again, at some point, I hope you'll be able to go just straight from the polynomial to the answer without writing all these other steps in, but for now I wanted to make sure everything was clear. I want to point out one other thing with this. Notice we started with a third order polynomial. The degree there is 3, and we ended up with the degree of 2. So taking the derivative does reduce the degree of a polynomial function. So here on the last one, we've got f of x is equal to 3x cubed minus 5x minus 12. What I want to do is let's see if we can find multiple derivatives. Taking the first derivative, again, we've seen this. We take the 3, multiply by the exponent of 3, gives us 9, and then we reduce that exponent by 1, so we get 9x squared. On this next bit, 5x, again, it's going to be a subtraction. I keep the 5. That exponent, again, you could think of that as being an exponent of 1. Multiply that in the front, subtract it on the exponent. We end up again with just a negative 5. So please notice that anytime you have taking the derivative of something like 5x, you end up with just 5. The variable ends up going away. And then finally at the back there, the derivative of 12 is just a 0. So this, of course, would be the first derivative. But now let's take the derivative of that. So I want to take the derivative of the first derivative. Notice the notation for that. Here I have 2 little marks there for the derivative, 2 little prime notations. So what do I do? Well, I'm now going to take the derivative of 9x squared minus 5. Again, using our power rule, multiply that 2 in the front, gives us 18, and then subtract 1 from that exponent gives me just a 1, which I don't need to write. And then the derivative of 5 is 0, so I don't have any constants there at the end. All right, not so bad. This, of course, would be the second derivative. And now for the third derivative. Notice I now have 3 tick marks there. That is the third derivative, which means we're going to take the derivative of the second derivative. So I want to take the derivative of 18x. Again, we've seen this a few times now. If you've got 5x and you take its derivative, you just get 5. So if we take the derivative of 18x, we end up with simply 18. So this last little example here gives us an idea that we can have multiple derivatives. By the way, this last one was called the third derivative. Now we could continue on. I can take the fourth derivative and so on. But how do we denote that? Let me go over the notation for this. So if you want to take the derivative of a derivative, so if I take the derivative, so I've got f prime, I want to take the derivative of that. That's one way of writing it, just putting another prime mark outside of it. Just make sure that this prime mark here on the outside does not look like a 1. Okay? But we often just do a double prime mark for the second derivative. Another way of writing this, if it gets too much for the little prime marks, we'll use the number in parentheses. We do that so that it doesn't get mixed up with an exponent of 2. So this is saying, oh, it's a derivative. If you see that, what looks like an exponent in parentheses, that means it's a derivative. Another notation is to say we're taking the second derivative of f with respect to x, and that's saying it's respect to x both times. So this is all ways of saying the second derivative. So first derivative notation, second derivative notation, third derivative notation. And actually after the third derivative notation, we stop using the hash marks and we start using this little kind of superscript in parentheses. So in general, if I want the nth derivative, so if I want the fourth or the fifth or the sixth derivative, then we'll use this, whatever number it is, 4, 5, 6, on and on. Again, superscripted in parentheses. We can also use kind of a ddx notation, so it's the nth derivative of f with respect to x n times. So that would be the nth derivative notation. Hopefully that's not too bad though. Enjoy!